Okay. Is the screen visible?
Yes,
is the screen,
you are audible. Yeah.
Is the screen visible also?
Yes.
The screen is visible. Like this. Yeah.
All right. So let's continue from yesterday, where we had left. So we saw extensively how the spherical collapse model allows us to look at the possibility of nonlinear collapse, at least in the spherically symmetric case. And what was the key learning from that exercise was the fact that even when the overdensity field actually becomes highly nonlinear, you can actually have a extrapolation of your linear theory result and make reasonable predictions about formation of virialized objects. So that was the crucial thing. So we will again start from there, and because there is one thing that needs to be discussed in some detail. So one thing we have at the back of our mind is, of course, this overdensity field. But if you see, yesterday we spoke about the average of this in a certain spherical domain, right? Region. So we spoke.
Tapomoy, sorry, it got mute. You may need to unmute yourself and. Yes, you are audible now.
Is the screen also there?
Yes.
Okay. So what I was saying is that we will now put this suffix r to indicate that this average is over a sphere of radius r, and well, we'll just write it down from our last class. So we have this 4/3 pi r cube. I can write x, but yeah, it's r cube, and then it is just this delta x d cube x. Now we want to study this quantity in some detail. So basically, this is the average of this inner spherical volume. So the good thing to do is, and convenient also, to write this in Fourier space. So we do the Fourier transform and write this quantity delta in Fourier space. And what that yields us is the following. So we just write this as introduce the Fourier transform. So we have this d cube x integral, but now we have a d cube k by 2 pi cube delta k, which is the Fourier transform of delta x. And then, of course, we have the dx integral. So I write it here, e to the power minus I k dot x d cube x. And then I have a global 4/3 pi r cube. So I've just written delta x in terms of its Fourier transform delta k. And now we have this integral. And please understand this delta x, this is in this volume of a spherical volume of radius r. So this is an integral which we can actually perform. So we want to write this basically in terms of delta k. So what we have to evaluate is now this integral e to the power minus I k dot x d cube x in this region r. So this is a finite volume in which we have to do this integral. So we can choose a z direction, and thereby we can define the angles theta and phi just to write this volume element in spherical coordinates. So with that, this just will become these three integrals. So you have e to the power minus I k x cosine theta, and then I have x square dx sine theta d theta d phi. So this d phi integrates very easily. That's just a 2 pi, and you have this 2 pi, and you have two integrals to work with. So e to the power minus I k x cosine theta x square dx sine theta d theta. So this cos theta, if you call this cos theta as mu, So this x goes from 0 to r and 0 to pi. The cos theta, if you define as mu, then this theta integral just becomes integral over mu from -1 to +1. So then you have this as just 2 pi 0 to r -1 to +1 e to the power I k x mu x square dx d mu. So this mu integral can be done, like it's a straightforward integral, and you can write this solution, this integral actually in terms of sines and cosines, and you have a, so finally you have 1 by 4/3 pi r cube into the power -I k dot x d cube x is basically this integral. And when you divide it by 4/3 pi r cube, it's very simple. I'm not doing the integral. You will get this quantity, 3 by k cube r cube. You can see where this k is going to come from. It's coming from this k over here. So when you do the integral, that k will come in the denominator. And then you have inside sine kr minus kr cos kr. And we just give this a name. Since the kr is the argument, we can just write this as w of kr. So what we finally have is this result that the average delta, so we remember we started with this delta r bar is basically this integral, this d cube k integral is sitting outside by 2 pi cube. And we have finished the x integral, and then we have just delta k wkr. So you can immediately see that the expectation value of this quantity is going to be 0. So the expectation value of this is 0 because the expectation value of delta k is 0. And the crucial thing to understand is that this is actually of some physical meaning. So when we talk about a density field which is fluctuating, and we have some sort of a random field, I mean, what is the actual meaning of something being random and having some fluctuations? I mean, we also always talk about some sort of a smoothing, some kind of a smoothing scale over which we are making this kind of analysis, right? So because depending on the kind of smoothing that we do, for example, the kind of spheres we put and do this average, I mean, this field will have different values, right? So we have to think at the back of mind that there's some smoothing scale that we are talking about, and then we are looking at the average of this delta in that smooth over that scale. So the density field always has to be inherently thought of. There is some sort of a smoothing scale at the back and over which we are doing. So in this case, we are just doing this smoothing in a very in a spherical region. So we put these spheres and we find the average. So this is what is called the spherical top hat smoothing. Why does this appear? And you can clearly see this average is going to be 0 because this is related to delta k, and average delta k, this we had discussed, this is 0. And this expectation value, please understand.
Your screen has disappeared.
Oh.
Yeah. So can you just tell it again? Yeah. It's coming. Yeah. It's okay.
Right.
Yeah.
So please understand there are two averages happening here. So often there is a confusion. One is this bar symbol, which this bar is accounting for the averaging over the sphere. So this is basically the smoothing, whereas this angular brackets is denoting the ensemble average, right? So that is the thing that you have to understand. Okay, good. So now since the expectation value is of course 0, but we can calculate the variance. So this is the mean, so that we can calculate the variance, and that is usually denoted by sigma r square, which is the expectation value of delta r bar square. And that you can clearly see, since you know this, you can compute this. There will be 2 of this, you take the product, and you will have to take the expectation value of delta k and with another delta k, so that will give you a power spectrum. So this will be clearly d cube k 2 pi cube.
Yes, there is a question from Pasunda. Kusumda, please
Yes.
go ahead.
Yes.
Tapomoy, so the other average, which is the ensemble average, is also done over a certain region, right? Volume.
Yeah, but that is now doing this thing. I mean, you are now looking at this delta R at different places.
So the
Right, you
the
put
scale.
different spheres. You put different spheres in your box, and you do average on that, and then right. I can't hear properly.
Hello.
Yeah.
Yes, yes.
Yeah, the scale over which the first averaging is done is much smaller than the R here, is it?
We haven't yet spoken about the scale R. It is arbitrary as of now. We have put arbitrary spheres, but yeah, I mean, if this angular average has to make sense, I mean, if you average over the whole universe, you would get anyway 0 because you have reached the scale of homogeneity, right? So you have basically averaged over everything. So of course, this R has to be smaller. I mean, to make any sense, I mean, to get any fluctuation, you have to do the averaging over scales which are much smaller than the scale of homogeneity, for example. I mean, if you reach the scale of homogeneity, then you will have no fluctuations at all. Okay. So, I mean, clearly less than 100 megaparsec, right? That's okay, good. So now the sigma R square, which is the variance, though the mean is 0, this you can compute, and this will be now proportional to this power spectrum will come because of this one, and then this WKR square. So, I mean, we'll come back to this, but for the time being, this is going to be very, very important a quantity. So what it really measures is the variance of the overdensity field smoothed over a scale R. So that is the interpretation of this sigma R square. Very good. Now, of course, we have to now know this power spectrum. So what we have achieved is we have written this in terms of the power spectrum, now, which is very good because if we know what kind of power spectrum we have, we can actually compute this integral and estimate the value of this. So this actually is a cosmological probe in some sense, because if you could somehow measure this quantity sigma R square, which people do using galaxy clusters, and if you can actually measure this, then you can actually have something different. At least you can say something about the normalization of the power spectrum, which you can clearly see, because the rest is an integral. But of course, if the power spectrum has a normalization, that can be fixed by the quantity sigma square R if you can measure it. Now let's take a toy model and then see how to understand this sigma square R. So let's take, for example, this power spectrum to be a power law. So it's some k to the power n, say, and then you can immediately see what this how this sigma R behaves. So sigma R square then will be, by the way, if this is just this d cube k can be written as 4 pi k square dk, because this is only dependent on the magnitude of k. So with that simplification and the cancellation of the 2 pi's, etc., you will just get a by 2 pi square dk k to the power n plus 2. And that is this one of the k square comes from the 4 pi k square of this d cube k, and then there's k to the power n, and then you have wkr square. So let's see how this scales. We are more interested in the scaling of sigma R with R. I mean, instead of trying to work out the integral, we have to then, of course, substitute W and do the integral rigorously. But just to get a feel of the scaling behavior, we just want to write this thing in terms of a new variable kr, and you just call this y. So we just want to get the R information out. Okay, so this, instead of this dk integral, we want to write it as a y integral. So if you do that, this integral can be transformed. So in terms of this new variable, dimensionless quantity. So basically you want the entire dimensional objects to sort of come out, and the integral you want to make dimensionless. Okay, so with that, you just substitute and you get 2 pi square. And then this integral becomes this dy y to the power n plus 2, and then this w of y square, and then everything which has dimension, that is in R, that comes out as R to the power minus n plus 3. That's very simple because there's 2 from here and 1 from this dk, so R will be R to the power minus n. So you can immediately see that sigma R, at least for this kind of a power law with an index n, so this sigma R square goes as 1 by R to the power n plus 3. Okay. So you can immediately see that for n equals to -3, this sigma r is basically unity, order unity, which means fluctuations are same in all scales. So this is something which is very interesting, because when sigma r is unity, I mean, it's independent of r, which happens. So let me write that down, but it's important. When n equals to -3, you can immediately see that sigma r is independent of r, and which means that you have all scales basically. I mean, on all smoothing scales, you have the same fluctuation. The fluctuation is, there's no change in fluctuation on scale. Okay. Now one can write this down slightly. So this power spectrum is over here, right? So so if you look at the time dependence, so you should actually multiply this with the growing mode square, d square. So ideally you should have this written as a growing mode square sitting out. So we had not put that, but now we can write that down. So if you write sigma r square that way, so then you have basically d square, and then some amplitude of the power spectrum, and then this r to the power n plus 3. And there could be some factor, but I'm just giving the rough scaling behavior. So this is a very important thing to note, that if you see the condition for collapse, remember we talked about the formation of collapsed objects yesterday. So this variance, I mean, this is something like an ordered unity thing. So once this, I mean, it reaches some ordered unity, you can say that a collapsed object has occurred. So that would give us some sort of a scaling of the scale of collapse with the time at which it collapses. So the d square is something which is a function of time. So you can immediately see that sigma square ordered unity that occurs, and these are all scaling arguments. So I mean this is just to see how these things scale. So you can immediately see this d square in, say, matter dominated epoch grows as, so d is, say, growing as a. So you have a amplitude times a square r to the power minus n plus 3. This is ordered unity. Or you get r, so a is 1 by 1 plus z. So you get r proportional to 1 plus z to the power minus 2 by n plus 3. So that's an interesting result. So the scale which collapses and for a given index of the power spectrum has this kind of z dependence. So what it actually tells you, that if n is equals to -3, then all these scale collapse at the same time. Whereas if n is slightly larger than -3, you will have large redshifts. High redshifts will correspond to small r. So at high redshifts, small scale things would collapse, whereas at low redshifts, large objects will collapse. So which is what is something we know in cosmology called hierarchical structure formation, that at very early times, the first things that formed were small structures, and then big structures formed later at low redshift. So that is roughly that you can see, but you need index n, which is greater than -3. So small structures merge to form large structures. That picture of hierarchical structure formation, you can see when this power law of index is roughly slightly less than -3, and that is when this will happen. So then r is inversely proportional to z. So so I just wanted to mention this, because this, at least from this simple scaling, you can at least get a picture of hierarchical structure formation. Another important thing is that you need this sigma square r, as I said, to normalize the power spectrum. So what is usually done is this r is chosen to be H inverse MPC, and so which is usually denoted as sigma 8. And so this is, in fact, why this is chosen. This is roughly the scale where the fluctuations are becoming nonlinear. So all you need is one scale and at which you measure. And if you can measure this sigma square 8, you can use that value. And this is typically found to be something between 0.8 to 0.9, and not sigma square, sigma 8. And then this can be used to normalize the power spectrum. Good. Okay, now we ask ourselves the question. Of course, we are talking about the collapse of collapse of over density fields to form structures. The question that we are asking now is, can we use this idea, or that when the density reaches a certain critical density, there is a collapse to form structure. Can we use this to actually make a count of the kind of collapse structures that are formed? So let us ask this question of. So first thing is, we associate with a halo a virialized collapsed object, and which we discussed yesterday, is something which we can understand from spherical collapse model, happens at roughly around theta equals to 2 pi. But of course, the nonlinear theory gives a very large, almost unbounded value of the density, but the linearly extrapolated theory tells us that this happens when the becomes a critical value, and this is at delta bar equals to 1.68. So this is, of course, the linearly extrapolated. So you take the linearly extrapolated evolution of density fluctuations, and if that hits this value, then we say that a virialized halo is formed. So now we are interested in the question is, what is the number count? What is the number of such virialized halos that we can find in a certain mass range, right? So we know that when this collapse happens, it's happening. It has the mass that is contained in that sphere is what is the mass of that halo, right? So the question is, how many such halos we can find in a given mass range? That is a question we are asking.
Pramod, your screen has disappeared again.
I don't know why this happened.
Yeah.
So
Good.
So right. So now, so that is the question we are trying to understand. So let us see the picture. So let us see what is really happening. So we start with a density, initial density, some field, some delta at some t equals to 0, and we evolve it according to linear theory. So we get some new density field, right? And it's like there are over densities and under densities, right? So now if we look at this density field, so the places where this over density field has hit the threshold value, and this is linearly extrapolated, we don't have to do it, it's just linear extrapolation. So the moment that hits that threshold value, we say that a halo has formed there. But that is not the question that we are interested in. So of course the halo is going to be formed here. We are interested in a slightly different question. We are interested in saying how many halos are formed in a given mass range. So we are also interested in what is the mass of that halo that is formed. So the way to do that, way to identify that, is to first of all say choose a point. Okay, we choose a point in this density field, and we put this sphere at this point and calculate the average, right? So the point is we have to see that threshold value hitting that 1.68 at a certain value of the smoothing. Now, what is important is, whenever you talk about a density field bar, this delta bar, there is some smoothing at play, right? So what we have to understand is what is the size of the halo, or what is the mass of the halo. That we have to understand only when we look at this density field smoothed at different scales. And once, for example, we start with a very large scale over which smooth this. So of course, if the scale is very, very large, this density average will be 0, right? And then we slowly start decreasing the sphere over which we are doing the averaging. And then at the moment, of course, what will happen when we start changing the size of this region over which we are averaging, the value that we are getting at the center, that will keep jumping back between numbers, right? Because it will not neither increase or decrease monotonically, because at very large value of R, it will be 0. I mean, this bar operation, right? This bar operation is averaging over R. So once we do it over a very large scale, this will be clearly 0. But as we decrease the size of the sphere, what will happen is you would be averaging over some random field. So if the sphere sort of suddenly excludes the large under dense region, then there would be a sudden jump. But if it suddenly excludes a sudden over dense region, then there would be a fall. So this, as you keep changing the size of the sphere, this number will keep hopping. But at some point, you will hit an average value which is greater than the 1.68, the critical. So then you stop and say, okay, here is a formation of a halo, and this is the size of the halo. This is the mass of the halo. So we identify that as a halo of a certain mass and of a certain size. This is what we are trying to do. Okay, so please understand what we are doing. We have fixed one position. Now the position is fixed, and around the position, we are now changing this radius over which we are smoothing. Okay, and we are measuring delta of R. By changing this R, we are measuring delta of R bar at that point, and then seeing whether this value hits the critical density, which is the condition for collapse. So that is our prescription. Now, what are we varying? We are varying R. But what is conveniently done, instead of R, what we actually are going to vary is basically sigma square R, which is the same as R, because we just saw, in fact, our exercise shows that sigma square is monotonically decreasing with R. So one can use R, sigma square R. In fact, the three variables R, M, and sigma square R, they're all interchangeable variables, because R and M are directly related to one another, because M is just R proportional to R cube, and sigma square R is inversely related to R, right? So they're all basically measure of the size over which we are doing the averaging. So usually what is done, one plots at a given point. Please understand, we are doing this at a given point. We are varying. This usually is written as lambda, sigma square. So we plot lambda in this direction. Or in other words, we are plotting M or R in this direction. Same thing. So on the right hand side, you have large mass and large R. And on the left side, you have on the right side, you have a small m and small r, and m is 0, r is 0 as at this side, so it's 0 here and infinity here, whereas lambda goes in the opposite direction. And the y-axis is delta bar r. So this is what we're interested in. So let's see what do we expect. So when the r is infinity, what do you expect? Or which means sigma square r is 0, which is this point. What is the average? What do you think the average should be? Anybody? Very large scales. We are at a given point, we have chosen the huge size of a sphere, and we are averaging. What should you get for the value of the over density? It should be 0, because it's you have far greater scale of homogeneity is reached. So you'll start with 0, and then as you keep sort of decreasing the size, so as you go this way, you are decreasing the size of your spheres. So you would have the next point here, the next point here, you will have this kind of a jagged. Now you see why this is going to be this kind of a walk, because since we are averaging over something which is random, an overdense region might come into your radius, our underdense region might leave your radius. So we don't know what is going to enter when you're putting those spheres and successively reducing their size. So your point, the average will keep going up and down. Okay. So now it turns out, very importantly, that this is going to be a random walk, or basically like a Brownian motion, like a drunkard's walk. And what is a drunkard's walk? The drunkard's walk is basically a random motion of this, and now you can think of this lambda as something like a time, and this is, say, the displacement of the drunkard, and it is making a walk. The thing about pure stochastic processes, or Markovian stochastic processes in this case, is the fact that there is no memory. So at each point, it has no memory of its past. So that the next step that it takes is uncorrelated with its past step. So, but that is not going to be necessarily true, because these deltas, are correlated, isn't it? So The question is, when will I guarantee that my smoothing will lead to the behavior of this delta bar R as a function of R as a memoryless or a perfect Markovian stochastic process, which means at every step, it has no memory of its past. It takes the next step, which is uncorrelated with the previous step. It takes just a jump, which is uncorrelated with its entire past history. Now, that will happen if at each stage that I'm doing this average, I am adding my modes are, I mean, the fluctuations that I'm talking about, they cannot be correlated. If they're correlated, the steps would be correlated, right? If you put another sphere and if you do the averaging in such a way that your steps get correlated, then of course this random walk will not be perfectly Markovian. But now think of this. If we use a certain filter, so here what we are using is what is called a spherical top hat filter in real space, right? What we said. What we did was we chose spheres in R, and then we are doing the average. But now think of doing it in a slightly different way. Think of going to Fourier space. Now in Fourier space, you know fluctuations. If you go to some delta to delta, capital delta, then you know that these modes in K, they are independent, right? So instead of doing this filtering in real space, if we start to do filtering in Fourier space, which means instead of doing this from says R, we do it in K space. So we have some top hat filter in K space. What is it? What is that going to do? At each stage, you are basically including more and more K modes. Like here, you are including larger and larger radii. In K space, it would mean you are adding more modes, right? Of course, you have to Fourier transform. It would be some funny function in your real space, that filter function. But if it's a spherical top hat in K space, then what you are doing at each step, you are just adding more and more modes. But these modes are independent. So if the filter that you use is a top hat in K space, then the statement is then your walk is going to be a perfectly Markovian walk. So you would have, and this is a result which we shall be crucially interested. So we'll choose that kind of a filter to ensure that I have no correlation between the steps. That's an important statement. Now the question is, of course, this is happening. So my statement is as follows. The statement is I have some critical density. This is delta bar C, which is 1.68. And I have this walk. Please remember, this is lambda going this side and R or M going this side. So you have this kind of a thing. And the moment there is a cross, there's an up crossing, a halo is formed. And this is the mass corresponding to that halo. Okay. So the first up crossing of this walk with the critical threshold is identified as a halo of the mass corresponding to that. Great. Now you will ask what happens if there are multiple crossings. I mean, it's a random walk. No, it can cross many times. It can go below also. What does it mean if this is going below all completely below? I mean, it's not even growing. It just means it's a void. There's nothing there. So you take bigger and bigger spheres, the density keeps getting. You have hit a void. So all those things can happen. But anyway, so if you hit and if there are more crossovers, see, they correspond to smaller and smaller mass. So this is the largest halo that is there. And then these can be thought of as sub-halos, smaller. So usually one is interested in the bigger halo, which is out. So we count usually the bigger halo. If you're interested in sub-halos, then you can have to count these things also. But usually one is interested in the largest halo. Okay. So the first up crossing is of consequence to us. Now, please realize this is one random walk, which means we have chosen one point. We have some realization of the density field, and we have seen where it hits under this variation, under this evolution, under smoothing. Okay. So now what you want to do, you want to find the chance. What is the probability of mass M halo to form, which means you are interested in the probability of such a path which has a first crossing at M, which means you want to look at all possible random walks, right? You want to choose all possible random walks and think of many such random walks, and then see what is the fraction of those random walks which has first crossed this critical at m equals to n. So that would give you the probability, right? So that is what we are going to be interested in. So what is our interest? So the question we are asking is this: what is nm, which is the number density usually, but let's say number of halos per unit volume with mass between m and m plus delta m. I mean, it's a continuous probability, so you have to take a little bin in m and see the number of it. This is related to, directly related to the fraction of random walks that has a first upcrossing of the barrier between m and m plus delta m, or lambda and lambda plus m. And this probability we call f delta, I mean I could call delta bar, delta lambda d lambda. So this probability density is what we're interested in. And when I say fraction of random walks, which means we have to think of many realizations of the same density field, take the same point, for each of those realizations generate a random walk. So we have a whole ensemble of these density fields, and then generate these random walks by doing this smoothing. Say another realization would give this. So you start with different initial realizations of the density field, apply your smoothing, generate all these random walks, and then find the fraction of these random walks, and which is the probability density of the random walk to have the first upcrossing of the barrier between m and m plus delta, and that is this probability. So we are interested in this. And how is this related to our physical quantity of interest n of m? That is very simple. So if you consider some volume v of the universe, so and for a mass m halo, there will be volume of each halo would be something like m by rho bar. So the number of halos would be v divided by, so the n would be v divided by m by rho bar. I mean the total number I'm saying. And so number density would be something like rho bar by m, right? So basically this n m dm is basically rho bar by m, which is the total, times this probability density, f delta lambda d. Very good. So we are interested in this quantity, f lambda, because once we know this, we just multiply it with rho bar by m, and when we get the probability or the distribution of the halo in different mass bins. So our purpose is to find this f. Now here we shall now go through this process to this calculation to see how this works. Okay. First thing, so let's go systematically. So we introduced another quantity. So we are interested in this f. Remember what f is always. F is the probability of a random walk to have a first upcrossing of the barrier between m and m plus dm. Okay, or this. Now we introduce one more quantity, which is basically to say that, okay, let's say again we look at this random walks. Let's say there are different random walks. Now we are interested in the probability that how many of these, what is the ratio, what is the fraction of random walks which reaches this same spot? So what is the probability, or rather the fraction of random walks, which is basically the probability of random walks, which has reached this value, say I call this delta 0, this value, at lambda 0. So again, you consider many realizations and say what is the probability of the density field to have the value delta 0 when the smoothing is lambda 0. And this, you know, is a Gaussian. This is the definition of the Gaussian random field. If this is the variance of the density field and this is the value, then you know this is a probability distribution which is given by 1 by root 2 pi lambda naught e to the power minus delta naught square by 2 lambda naught. This is just the Gaussian distribution. But what is this? This is the probability that delta has value delta naught at lambda equals to lambda naught. I mean delta naught plus delta naught. I mean you have to use this because continuous probability distribution, right? So this probability will be so between delta naught and delta naught plus and delta naught plus delta naught at lambda equals to lambda. That is the probability which is given by this probability distribution. This is something which we know. This is our assumption that the underlying field is a Gaussian random field. Okay, now I'm going to make an important assertion. So this delta 0 is somewhere, let's say over here, okay? Now, any random walk which reaches this delta 0, let's consider another cut threshold, which I call delta 1, which is less than. So let's consider another cutoff, which is I call delta 1, which is less than delta 0. Okay, so the statement I'm going to make is the following. All the trajectories which have reached this delta equals to delta 0 must have at least upcrossed this delta 1 once. It could have crossed it many, many times. Because delta 1 is less than delta 0, it must have upcrossed it once, right? So here is an important statement. So that we consider, I mean, we are going to use what is called the translation in invariance, okay? And that's what we are aiming at. So we now consider another delta 1. And we are going to say that all trajectories, trajectory here means the random walk with delta equals to delta naught and between delta naught and delta naught plus delta naught must have upcrossed delta 1 less than delta naught at least once, right? At least once it must have crossed this other threshold which is below. Okay, so now let me write this down mathematically. So what I'm saying is this probability of delta to have a value delta naught at lambda naught, which is what this Gaussian is, right? This must be thought of as happening of two things. Delta has reached delta naught and delta has upcrossed delta 1 at least once. I mean, this implies it has to be both of these, right? So this is basically intersection. I mean, these are two events, right? Delta has reached delta naught and delta has upcrossed delta 1 at least once before. So this must be, now you can use probability of A and B equals to probability of A times probability of B given A. It's just probability theory. So what you have is very simple. So this probability of delta naught having the value delta naught at lambda naught must be equals to this probability first upcrossing at delta 1, and you know that by definition is F. So I'm going to write D delta naught. This is F delta 1 lambda 1 D lambda 1 times this probability of delta naught lambda 0 given delta 1 lambda 1 first crossing. Probability of A and B equals to probability of A times probability of A given probability of B given A. So this is very good because now this is what we're interested in, huh? This is what we know. So all we need to now know is this. By the way, this delta 1 which is below delta naught could be anywhere. All that matters is that it should be less than the delta 1. So it could be anywhere. So I really don't care where this this intermediate lesser threshold is. So what we can actually, or where this lambda 1 is actually. So we can actually completely this lambda 1, which is this one, delta 1 lambda 1. So this delta 1, lambda 1, this could be anywhere. So this lambda 1 could be anywhere because that upcrossing could have happened anywhere, but it can only happen between 0 and lambda 0. So lambda 1 can be between 0 and lambda 0. Okay. So we don't care where this lambda 1 is. So we want to integrate it over it. So the actual thing is it could be anywhere. So it is this or that, or lambda 1 could be anywhere. So basically we have an integral. So this is for a given lambda 1, but basically we can integrate it out because lambda 1 could be anywhere. So basically you have this given by d lambda 1, and lambda 1 equals to 0 to lambda 1 equals to lambda naught. It could be anywhere in between. And then you have this probability. So you have f delta 1 lambda 1 first crossing d lambda 1. Sorry, I've already written d lambda 1 multiplied by this quantity, probability of delta naught lambda 0 given delta 1 lambda 1 first crossing. This is what we now need to know. On the left hand side, you have probability of delta naught at lambda naught d delta naught. And we are interested in this f, mind you. Okay. So we have integrated over lambda 1 from 0 to lambda 0, but we want to understand this. Now, this is very important. You see what this is. This is the probability that you start from a point which has delta equals to delta 0 lambda 0. Delta 1 lambda 1 and go to delta 0 lambda 0. So you start with delta 1 lambda 1 and go to delta 0 lambda 0. Now here we use the fact that this is actually a Markovian process. So the origin does not matter. The random walk does not have any memory of its past. So at any point, you can think of it as the beginning of the random walk. This is the origin of the random walk in the picture, right? This is the origin which I've marked over here. But this is not necessary. You can choose any point as the origin, and the random walk is exactly the, I mean, it has no connection with the past. So this probability is basically that you start from delta 1 lambda 1 and reach delta 0 lambda 0. But delta 1 lambda 1 you can now think of basically as the origin. That probability of starting from this point and going to this point is basically saying that the origin, instead of being 0 0, is now delta 1 lambda 1. Now we already know probability of delta 0 lambda 0, right? But we don't know this delta 1 when the origin is shifted to delta 1 lambda 1, but that's just a shift. So this quantity, and this is the most crucial step, this is basically, this conditional probability is nothing but 1 by 2 pi. It's just a shift. So it's basically square root of 2 pi, square root of lambda 0 minus lambda 1, e to the power minus delta 0 minus delta 1 squared by twice lambda 0 minus lambda 1. So what I've done is I've just shifted the origin to delta 1 lambda 1, and then it's the same probability distribution. And this is possible. You can do on this only when it's a actual random process, which is Markovian. Very good. So now we have all the prerequisites. Now we have everything. So now I have this function. I know this function. All I need to is to scoop out this f. Now that is just algebra. All the physics has been put. So let me write that down. So we have probability of delta naught lambda naught d delta naught. This is equals to integral 0 to lambda naught d lambda 1 f of delta 1 lambda 1, and then you have an e to the power minus this quantity delta 0 minus delta 1 square divided by twice lambda 0 minus lambda 1, and there's a factor 1 over 2 pi lambda 0 minus lambda 1. Now there's just manipulation. I need to scoop out this f out of this integral equation. That's not very difficult in this case because there's a trick. These are all probabilities. So once they integrate it out, you get numbers, right? So that, and it's a Gaussian. This is a Gaussian, this is a Gaussian. So one can integrate it out and then you can get something. So what we do is we integrate this left hand side basically, and just a trick, you just integrate it from delta 1 to infinity, just for convenience. And then you have p delta 0 lambda 0 d delta 0 equals to this integral d delta 0 delta 1 to infinity d lambda 1 0 to lambda 0, and then you have f delta 1 lambda 1 e to the power minus delta 0 minus delta 1 square by twice lambda 0 minus lambda 1. And then there's this factor 1 by 2 pi lambda 0 minus lambda 1. I mean, this integral from delta 1 to infinity is just for mathematical convenience. I just want to write everything in terms of what is called an error function. It's just using Gaussian properties of the Gaussian. Okay, and now it's very simple. We just change these variables, delta 0 minus delta 1, and we can finish off this integral with this delta 0 integral. So you have a few things to understand over here, that if you call delta 0 minus delta 1 as some xi, I'm just calling it a new variable, then you have this 0 to so this delta 1 to infinity integral will become now 0 to infinity integral, and there will be a d xi e to the power minus xi square by twice lambda 0 minus lambda 1, right? And 1 by 2 root 2 pi lambda 0 minus lambda 1. I'm just writing this integral. That f integral I'm not writing. So this other integral, this one with this one, I just want to finish that first. That integral is just half. That's just equals to half. So what you have is, by doing this integral from delta 1 to infinity, what you have is this identity, delta 1 to infinity. And this is Gaussian integrated from 0 to infinity, half. It's like a Gaussian function integrated from 0 to infinity. So it's this area, which is half. So you have delta 1 to infinity, p delta naught lambda 0 d delta naught equals to half times this integral over f now, lambda 1 is 0 to lambda 0, d lambda 1, f of delta 1, lambda 1. So now we have finished. Good. This, this is a Gaussian distribution. You can write it in terms of the error function, and that is not difficult at all. So what you can now show is that if the error function, if you know, is defined as integral from 0 to, so this is a definition of an error function. I'll just 2 by root pi 0 to say some alpha e to the power minus x squared dx. This is called error function of alpha. So with that definition, you can write this thing on the left-hand side as an error function, because this is a Gaussian. I have to change you have to write it as 1 minus, you have to change the integration limits, but that is, it's from delta 1 to infinity. So you have to shift it to delta 1 and sort of adjust that. So with that, what we will get finally is this result, that integral f, which we have on this side, f delta 1 lambda 1 from 0 to lambda 0 d lambda 1 will be equal to 1 minus error function of delta 1 by root twice lambda 0. Just using the definition. So I want f, so I have to just integrate. So what I will do is I integrate with respect to this, differentiate with respect to this upper limit. So I take a dd lambda 0 on both sides. Standard technique. So what you have is, when you take the dd lambda 0, you evaluate the integrand at that value. So you will basically have f delta 1 lambda 0 will be equal to now this quantity, derivative of this thing, and that is, what the error function is, right? Which is the definition. So you would have it's basically dd lambda 0 of minus 2 by root pi integral 0 to delta 1 by root 2 lambda 0 e to the power minus x square dx. And that if you evaluate, you will get delta 1 by root 2 pi lambda 0 cube e to the power minus delta 1 square by 2 lambda 0. So that is your f delta 1 lambda 0. So we have obtained what our goal was. So this is basically what is called the Press-Schechter mass function, because now you can write in terms of, so n will be and you can write it in terms of nm dm. You can now convert. So you remember you had a rho bar by m, and you can now convert this lambda naught. So lambda, you write lambda naught as sigma square, which is a function of m. So if you take that thing into consideration, this just will be root 2 by pi delta c by sigma m square e to the power minus delta square. Now, of course, you have to put this delta 1 equals to delta critical now. Delta 1 is the barrier that we are talking about, right? And that we put at delta c, because our barrier is the critical, and which is 1.68. So you put delta c instead of delta 1. Delta c square by 2 sigma m square d sigma dm. I'm just converting from lambda to sigma, which is 2 sigma d sigma d. So we are using d lambda equals to twice d sigma 2 d sigma times sigma, which is d sigma dm dm. So this I have used and put. So this is basically the celebrated Press-Schechter mass function. It actually tells you how many halos of mass m will be there in between m and m plus delta m. So this is slightly lengthy and slightly terse derivation. So let me just quickly revise the main steps to get so you can understand what is really going on. What we are step by step, we are interested in the number of halos per unit volume between mass m and m plus dm, which we have seen is basically proportional to the fraction of random walks. And what is this random walk? The random walk is the change of delta as you change the smoothing scale. And for a sharp k-space filter, so if the k-space has a spherical top hat, then you would actually have uncorrelated steps. It would be a perfect Brownian motion. So that probability, which is the probability of first up crossing of the barrier, the critical density between m and m plus dm, we call it f, and which is what we're interested in. This f is related to this halo mass function by this conversion rho bar by m. How do we do this? We introduce one more probability, which is the probability of the density field to have a value delta 0 when the smoothing scale is lambda 0, which is p d0 delta 0 lambda 0, which is a Gaussian. Now, this probability, the probability to have the value delta and lambda, has to have come by an upcrossing of a previous threshold at a lower value. So we take that condition, that probability of the density field to have a value delta 0 must be coming from a previous up crossing of a lower barrier, which is f, and this conditional probability. This conditional probability, what it does is basically shifts the origin of my walk from 0 to this new origin delta 1 lambda 1. So it's the same function. It's the same function, but with a shift. It's a shifted Gaussian. And then the rest of it is algebra. You use the fact that these are normal Gaussian distributions, so you can use their area under the curve. Half of, from 0 to infinity, it is half, and that's why we get this error function. And then basically you use it to find the halo mass function f. So this is actually a very powerful quantifier, because in cosmology, this is very, very well, you can constrain this very well. And in fact, by the way, this delta c that you have here is basically what we borrow from spherical collapse model, the linearly extrapolated density field at collapse, which we call which is the value 1.68, that canonical value which we are always using. But please understand, actual density field might be far more nonlinear. We are not interested in that. So this delta c is basically what we get from the spherical collapse model. Of course, if you use some other models, you would have to change your entire formalism. because your barrier then would not be so trivially constant. So if it would be some changing barrier. So here the barrier just remain constant at delta C, but that won't be true for a general collapse, which is non-spherical. So those generalizations are done. There are ellipsoidal collapse and things like that, and modifications to the press sector. But this mass function is very important, and it has also been very important to constrain it. So this is one of the things which people can measure, and apart from other cosmological things, this is something which you can constrain to a large degree. So I'll stop here and take questions.
Okay. So I don't see anything in the chat box yet.
Yes, Tapomoy, I have one question.
Yeah.
Yeah, I think this Brownian motion, can you repeat the argument? This argument of Brownian motion, I think you are.
So when you have random walk, the steps in general are correlated.
Right.
But I want it to be mimicked by, I mean, I want this process to be perfectly Markovian, so that I can use this conditional probability. I can just replace it by the same, but with a shift. So probability of delta 0 lambda 0 given delta 1 lambda 1 should be just obtained as the probability of delta 0 lambda 0 with the origin shifted to delta 1 lambda 1, which means the memory of that walk is not there.
No,
okay. Now, but I want
fine.
to do that. Now to do that, if I use any arbitrary smoothing, it will not happen, because then the steps will be correlated.
Right. Okay.
But yes. I want to insist that it is Markovian, so that I can use this probability as the same probability except for a shift. So how do I do that? So I want to ensure that my filter is such that at each stage of increasing my filtering size, the modes that the modes that are added, I mean are basically they are independent. So if I do it in K space, if I do the filtering in K space, so what I do is I have a box in K now. I have a top hat in K space. Okay. So when I use this K and increasing the size of that K space box, I'm basically adding in K. Adding in K means adding one wave at a time.
Right.
When I add one wave at a time, then I'm actually guaranteed that what I'm going to get is going to be independent, right? Because each mode is independent. But that would require me to do the top hat thing in K space. So when I come back to real space, it would be some funny function, convolution of that. So it's not the the top hat in a sharp cutoff or sharp what is called the sharp cutoff in K space. So a top hat in K space is going to lead you to this this filtering is going to lead you to the fact that my walk is going to be Markovian.
Okay.
I mean, does that answer the question?
Yes.
Any other question? Please raise your hand. Okay. I don't see any other question. I mean, not just from this talk. I think Tapomoy will be happy to answer if you have other questions from the previous 3 lectures as well in this now. Okay, excellent. If there is no other question, then we can stop here. Of course, the discussion can continue over the Slack channel. Thank you, Tapomoy, for this lecture and this series of lectures. And so we will meet for the afternoon session. We will, so we'll wrap up this session now, and we meet for the afternoon session. Thanks, everyone. Anjan,